Okay, so what we're starting today, and we will finish next class, is we're actually going to start calculating probabilities now. So we're going to look at some vocabulary today. What is a probability model? And you're going to learn some of the basic rules and notation. And then next time we will dive into it a little bit more. This is what you are looking for. So the last thing we did was we designed simulations. And we said we design a simulation so that we can estimate a probability when we don't know how to calculate that probability otherwise. And we talked about the more trials you do, the better. If you do more trials, your probability should approach the true value. Today we're going to start learning some of the theoretical rules. So here's the first example. This table right here is called a probability model. So we are going to randomly select a student that took the 2015 AP Stats exam and record the student's scores. Here is the probability model. So it's a little funky, but 0.252 of the students got a 3. So about a quarter of the students got a 3. 0.134 of the students got a 5. So about 13.5% of the students got a 5. If we look at part A, find the probability that the chosen student scored a 3 or better. You need to show your work. So what I'm going to do is I'm going to find the probability that the student scored a 3, add the probability that the student scored a 4, add the probability that the student scored a 5. And we get 0.578. And then just as a review from last time, if we were to interpret that probability, we would say something like in the long run, if we chose many students, about 57.8%, or we could also just use 0.578 of them, would have scored 3 or better. Okay, so in B, find the probability that the student didn't score a 1. That means that the student scored a 2, or a 3, or a 4, or a 5. Now, I'm lazy. I want to be efficient. Rather than add all of those up, what I can instead do is if these are the only possibilities, those are going to sum to 1. So if those are the only possibilities, they're going to sum to 1. So what I can do instead of adding up all 4 is I can just take 1 and subtract the only case that I'm not interested in. So the only one I'm not interested in is that the student scored a 1. So then the probability that the student didn't score a 1 is 0.764. That's what I would have gotten if I'd added up 2, 3, 4, and 5. Okay, questions, comments? Okay, so some vocabulary. First term we need to talk about is sample space. The sample space is the collection of all possible outcomes. So for example, if you flip a coin, your sample space is just heads and tails. Those are the only two options when you flip a coin. Now, of course, we're going to be looking at some examples that are a little bit tougher than that. Bless you. So we're going to look at this example. A library has 5 copies of a certain textbook on reserve, of which 2 copies are first printings and the other 3 are second printings. A student examines these books in a random order, stopping only when a second printing has been selected. Okay, so let's picture what this really looks like. So we have a shelf that has these 5 books. So we have book 1, we have book 2, we have book 3, we have book 4, and we have book 5. And so we have a student who's choosing a random book off of the shelf. For their first choice, how many options are there? 5. Okay, so rather than listing these out, because the student is choosing more than one book, I'm going to use what's called a tree diagram. So that's what I'm going to start drawing. So the student is going to draw one book first, and there are 5 options. So when I'm displaying the sample space, the student can either choose book 1, book 2, book 3, book 4, or book 5. So 1, 2, 3, 4, 5. Okay, so now it says, the student examines the books in a random order, stopping only when a second printing has been selected. If the student chooses book 1 off the shelf, is the student going to choose again? If the student chooses book 1 off the shelf, is the student going to choose again? Yes, because book 1 is a first printing. Now, they've chosen book 1 off the shelf already, so now the only options are 2, 3, 4, and 5. So off of that 1, the only options now are 2, 3, 4, and 5. Likewise, if the student chose book 2, they're going to choose again. This book 2 is a first printing, so we're going to choose again. This time, though, the options are only 1, 3, 4, 5. If the student chose book 3, are they going to choose again? No, right? Books 3, 4, and 5 are second printings, so if the student chooses those, that's it, they're done. Okay, so if we go along this branch 1 again, if the student chooses book 1 and then book 3, they're done. Book 1 and 4, they're done, because they've gotten the second printing. If they choose 1 and then 2, though, they have to choose again. You follow me? How many options are there then if they choose book 1 and then book 2? 3, right? 3, 4, 5. I'm kind of running out of room. Hopefully you have more. So 3, 4, 5. And then the only other time that the student is going to choose again, if they choose book 2 and then book 1, they have to go again. So 2 and 1, they have to go again. They would get 3, 4, 5. So this is one way of displaying the sample space. If you didn't like that way and you wanted to list it out instead, you could list out all of the options. So the first option, 1, 2, 3. So 1, 2, 3, 1, 2, 4, 1, 2, 5, and so on and so forth. And this just means first book, second book, third book. First book, second book, third book. Now, if you were asked how many options are there, we would have to count when all of these end. So I'm going to do that in red right now. So if I were asked how many options, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So there are 15 possible outcomes. That is something that you don't have to count up now, but you're going to have to eventually when we start calculating probabilities. So either one of these is a correct way to display the sample space. As a tree, that's fine. Writing out the outcomes, that's fine also. Okay, we are going to use this tree now in parts B and C. So B, what outcomes are contained in the event A, that exactly one book is examined before the experiment terminates? Okay, so all we're doing is looking at all these red outcomes, and we're finding the ones where exactly one book is examined. That only happens here, here, here. So if the student happens to pick book 4 off the shelf first, they're done. Book 3, they're done. So the only outcomes then are if they choose 3, 4, or 5. Okay, and then part C. What outcomes are contained in the event C that the chance experiment terminates with the examination of book 5? So again, we're looking at all of those red outcomes. We're finding the ones that end with book 5. So I'm going to do that in green. Ending with book 5 is here, 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 and here. So if I go in order from top to bottom, to get to here, that's book 1, book 2, book 5. So that'll be 1, 2, 5. This second 5 is just 1 and 5. The next one is 2, 1, 5. And then I get 2, 5, and 5. Do the best that you can with those curly brackets. The curly brackets just mean that this is a set of outcomes. Questions for me? No? Okay. We're going to finish this page, and then that's it for today. So, what is a probability model? Probability model lists all possible outcomes with their associated probabilities. And in order for it to be legitimate, those probabilities are going to add to 1, like our first table did. All of them together have to add to 1. Okay, what is an event? An event is a subset of the sample space. So it's a collection of certain outcomes. So for example, I could say, what is the probability or the event that when I roll a die, I roll an odd number? Odd number is an event then. It has some collection of all the possible outcomes. In this case, 3 of them, 1, 3, 5. Okay, 5 basic rules. The first rule is the probability of some event A is going to be the number of outcomes in A divided by the total number of outcomes in your sample space. Now, one little caveat. That is true only if all outcomes are equally likely. So for example, that example above, rolling an odd number. Odd number could be 1, 3, or 5 out of all 6 numbers. So we would say that probability is 3 out of 6, but only if all the numbers are equally likely. If it's a loaded die where one number is more likely than another, we can't just say the probability is 3 out of 6. Second rule, you've already seen this one. Probability is always between 0 and 1. That's why I don't want us to say the probability is 75%, 0.75. Next one, probability of all outcomes. We denote that with P of S. S is the sample space. Those all have to add to 1. Right? If I look at all the possible outcomes, their probabilities have to add to be 1. Okay. The probability of not some event, so the probability of not A, is 1 subtract the probability of A. We already did that on the other example. Rather than calculating not getting a 1, we took 1 and we subtracted the probability of getting a 1. And then last rule is if A and B, so these are two events, are mutually exclusive, which we're going to talk about in a minute, then the probability of A or B is equal to the probability of A, add the probability of B. Now, people mess this one up. This is only if the events are mutually exclusive. So that's very important. We're going to talk about what that means. But A or B is A add B only if the events are mutually exclusive. If they're not, then there's another way to calculate it that we'll deal with at another time. Last minute of your time, what I need to talk about is the last thing. What does it mean if two events are mutually exclusive? The other word for this is disjoint. If they are mutually exclusive, the events cannot happen at the same time. So in terms of a Venn diagram, because you're going to use Venn diagrams, we would say these two events, A and B, are mutually exclusive. If I were to look at a Venn diagram like this instead, the one on the right, A and B, are not mutually exclusive. And that's because right here, they can happen at the same time.